The speed of onset of volatile anesthetic agents and how quickly adequate depth of anesthesia is achieved is determined by a key principle in chemistry and anesthesiology, and that is the solubility of the agent in blood. It's determined by the blood gas partition coefficient. Fundamentals of Anesthesiology with me, Pat Nelligan. Understanding gases and vapors. The solubility of anesthetic agents in blood and tissues. This tutorial will look at the solubility of volatile agents and gases in blood, the blood gas partition coefficient. In the previous tutorial, we looked at what is anesthesia, anesthesia strategies, inhalational, intravenous, and combination, the history of volatile anesthetics, why sevoflurane reigns supreme, nitrous oxide as a second gas, and TIVA. In this tutorial, we're going to look at the solubility of anesthetic gases and vapors in blood and plasma, the blood gas partition coefficient, the solubility versus time of onset, other factors that impact onset speed, the FA divided by FI, overpressure, and steady state. When a gas exists above a liquid at a given temperature, some of that gas dissolves in the liquid. The quantity of gas that dissolves is determined by its partial pressure, the driving force, and how soluble the gas is in the liquid's storage capacity. This, of course, is Henry's law. Now, once that gas molecule is in the liquid, you can measure its concentration in millimoles per liter. But the gas molecules try to escape the liquid, and the tendency to escape is measured as partial pressure. Remember, there are no gas bubbles in the liquid, just molecules dissolved one by one. Gases are distinguished from other dissolved particles such as electrolytes because of their tendency to escape the liquid. Both can have their quantities measured in millimoles per liter, but because of the volatility of gases and the fact that they do not remain confined to the liquid phase, there is an equilibration between phases, and that is measured as a partial pressure. And partial pressure gradients exist between liquid and gases, within liquids, and between adjacent liquids. Of course, as we have previously seen, that is how oxygen and carbon dioxide move from air to blood and from blood to mitochondrion and vice versa. Gases cannot exert partial pressures while dissolved in liquids. When we speak of partial pressures, we mean the partial pressure of gas that would exist in the gas phase in equilibrium with that liquid. Equilibrium means that the number of molecules of gas that are leaving the liquid is equal to the number entering. The partial pressure in the gas phase equals the partial pressure in the liquid phase defined via equilibrium. Concentration refers to how much gas is in there in millimoles per liter. Partial pressure is how badly it wants to get out. The amount of gas dissolved at equilibrium is determined by the partial pressure of the gas, the driving force, the temperature, because warm liquids hold less gas than cold liquids, the solubility of that gas in that particular liquid, its solubility coefficient. A solubility coefficient tells you how many gas molecules will dissolve in a given liquid at a given partial pressure and temperature. The lower the number, the less soluble the gas. Its concentration is alpha times the partial pressure. In this case, alpha incorporates temperature dependence, chemical interactions with the solvent. These hold molecules in solution, and protein and lipid solubility. Let me give you a couple of illustrations. Imagine this guy is a gas. On the left-hand side, he is insoluble. He finds the cold water to be inhospitable and does not want to be immersed in it. On the right-hand side, he's sitting in a jacuzzi with a beer or another beverage. He's very comfortable and he doesn't want to get out. He is soluble in that liquid. This is an illustration of sevoflurane and its solubility in blood. Sevoflurane is highly insoluble in blood. It just does not want to immerse itself. Here it is sitting proudly of the other molecules in blood. Conversely, methoxyflurane is highly soluble and it's being dragged into the blood by these hands and they're clasping it, preventing it from escaping. The Ostwald solubility coefficient is described by lambda. It's a historical convention used to denote solubility in partition coefficients, and it persists in anesthesia. It's a dimensionless measure that describes the solubility of a gas in the liquid. It is the ratio of the volume of gas at a specified temperature and pressure dissolved in a given volume of liquid when the gas and liquid phases are in equilibrium. Now, this seems to imply volume of gas in a volume of liquid, but that's not the case. The term volume of gas refers to the equivalent volume that amount of gas would occupy in the gas phase at the stated temperature and pressure. The volume is used as a proxy for the amount of gas molecules dissolved, not physical gas bubbles in the liquid. At a fixed temperature and pressure, gas volume is directly proportional to the number of molecules, so the definition really describes concentration. A partition coefficient represents the ratio of concentrations of gas molecules in two phases, for example, between alveolar gas and blood once their partial pressures have equalized. Concentration refers to the amount of gas molecules dissolved per unit volume in millimoles per liter, whereas partial pressure is measured in kilopascals or millimeters of mercury. In this series, we will focus on three partition coefficients. The first is the blood gas partition coefficient that describes the uptake of volatile agents into blood. It represents blood solubility. The second is the oil gas partition coefficient that is used to describe drug potency, based on the concept that high lipid solubility translates to high brain solubility. And finally, the tissue blood partition coefficient that describes the uptake of agent into various tissues in the body, including muscle and fat. So let's move on now to the blood gas partition coefficient. The blood gas partition coefficient is defined as the ratio of the concentration of a gas in blood to the concentration in alveoli when the partial pressures are equal. The higher the coefficient, the higher the solubility in blood. And this is the key point that all anesthesiologists must understand. The lower the blood gas partition coefficient, the more rapid the onset of anesthesia. This is the list of the most commonly used volatile agents over time and their blood gas partition coefficients. We start with ether and we finish with desflurane. Note the enormous numbers for ether and methoxyflurane. That number is 12. What does this mean? It means that for every 1 unit of anesthetic in the alveolar gas, about 12 units dissolve in the blood. That indicates that these agents are highly soluble. As you move downwards with progressively newer agents, the numbers fall dramatically until for every 1 unit of alveolar volatile agent, only 0.42 liters of desflurane and 0.47 liters of nitrous oxide are dissolved in blood. These are highly insoluble, and that means a more rapid onset of action. Just observe the massive difference between methoxyflurane and sevoflurane. For sevoflurane, the blood gas partition coefficient is approximately 0.65. That means that at equilibrium, at the same partial pressure, the amount of sevoflurane molecules dissolved in 1 liter of blood is equivalent to the amount of sevoflurane that would occupy approximately 0.65 liters in the gas phase at the same temperature and pressure. For methoxyflurane, that is 12 liters. To put this into simple perspective, with low blood gas solubility agents, the blood behaves like a thin pipe. It cannot hold many anesthetic molecules, so blood concentration remains low, partial pressure rises quickly, and the partial pressure is rapidly transmitted to the brain. With high blood gas solubility agents, the blood behaves like a large reservoir. It can absorb substantial amount of anesthetic molecules. Blood concentration becomes high, and this delays the rise in brain partial pressure. Let me illustrate this. Partial pressure reflects the tendency of the gas to escape from one realm, the blood, and enter the other realm, the brain. For sevoflurane, even though the blood concentration is low due to low solubility, the partial pressure is high because it wants to get out of the blood, so molecules rapidly move. Methoxyflurane molecules are very comfortable in the blood, like the guy in the jacuzzi. They don't want to escape even though the concentrations are high, so the partial pressure is low and the uptake to the brain is slow. Anesthetic effect is determined by the partial pressure at the site of action. Large quantities of anesthetic may be present with little effect if the partial pressure is low. Brain anesthesia occurs only when brain partial pressure rises sufficiently. Solubility delays this rise for highly soluble agents. That's what you absolutely must know. Now let's put all of this together into an important concept, the FA to FI ratio. The key point that every anesthesiologist must know is that the higher the agent's alveolar partial pressure, the more rapid the onset of anesthesia. When we deliver inhaled anesthetic agents, the inspired concentration really only reflects what the alveoli are seeing, not the brain. But the gases rapidly pass around the circulation and return to the alveoli, and we are able to estimate brain concentration by looking at expired gas concentrations. When we are talking about gas delivery and gas measurement, we speak in percentages. For example, we deliver 30% oxygen to our patients. It keeps things quite simple. So volatile agents and nitrous oxide are always measured in percentages. The FI volatile agent is what you dial up on your vaporizer either manually or digitally, and you set the inspired percentage. The expired percentage is measured dynamically as gas returns in exhalation. In pharmacological terms, in the textbooks, it's known as the FA agent, the alveolar concentration, and the FA-FI ratio determines the speed of onset of the agent. It tells you how quickly the alveolar partial pressure is approaching the inspired partial pressure. So we can actually make curves of all of this. FI being the inspired anesthetic fraction or percentage, FA the alveolar anesthetic fraction. It describes the rate at which the alveolar concentration approaches the inspired concentration. So for low blood gas solubility, you'll see a rapid rise. For high blood gas solubility, a low rise. Remembering that the alveolar partial pressure reflects the brain partial pressure. So let's go through the setup for the FA-FI curves. Two axes, the y-axis, which is the FA-FI ratio, and the x-axis that represents time in minutes. We start off here at 0, that's patient is awake, all the way up to full equilibrium, where the inspired and expired volatile agent are equal. We're going to draw two lines here at 0.6, 60% of the ratio. That's where patients tend to lose consciousness, and about 0.8 or 80%, that's adequate depth of anesthesia for surgical incision. We're going to draw two curves now. The first one is the green curve and the second is the red curve. And what's critical here is this distance between the curve and 0.8. That represents speed of onset of anesthesia. The closer the curve is to the FA-FI line, the less soluble the drug is and the more rapid the onset of action. So we can tell by looking at this that the green line represents a drug with a low blood gas partition coefficient, and the red line is an agent with a high blood gas partition coefficient. Now, let's look at the FA-FI curves for various anesthetic gases and vapors. This looks like a slightly cluttered chart, but I want you to take note of a few things. First, at an FA-FI ratio of 0.6, I have drawn the loss of consciousness line. At 0.8, we have adequate depth of anesthesia, and at 1, we have something that I will discuss later in this tutorial, brain alveolar steady state. The agents are color-coded. Methoxyfluorine is green, halothane red, enfluorine orange, isoflurane purple, sevoflurane yellow, desflurane blue, nitrous oxide black. Note that nitrous oxide can never give general anesthesia alone. We'll discuss that in a later tutorial, but it does have a blood gas partition coefficient. The less soluble agents hug the y-axis due to their low blood gas partition coefficient, and they achieve adequate depth of anesthesia rapidly. So desflurane, sevoflurane, and to a lesser extent isoflurane are very rapidly acting agents. If you look carefully, nitrous oxide seems to work faster than desflurane. Wait, you might say, doesn't desflurane have a lower blood gas partition coefficient than nitrous? It absolutely does. But what determines Fa divided by Fi are four things. Blood gas solubility, as we've already discussed, alveolar ventilation, we'll get onto that in a minute, cardiac output, and the inspired concentration. And the last is really important for nitrous oxide. It is delivered in massive quantities, 50% or more. Hence, the speed of uptake is much more rapid than, for example, for sevoflurane that tops out at 8%. Blood rapidly absorbs large quantities. This causes the alveolar volume to shrink, the remaining alveolar gases to become concentrated, in particular nitrous oxide, the concentration effect. So the massive uptake of nitrous oxide makes alveolar nitrous oxide concentration rise faster. And we'll talk about this in detail in a later tutorial. This is the FA-FI curve for sevoflurane in yellow versus halothane in red. You'll note that the sevoflurane is nudging up almost against the y-axis, whereas halothane is falling down. And the reason why is that sevo is a far less soluble drug in blood. As a result, it gets to loss of consciousness and adequate depth of anesthesia much quicker. And I think this demonstrates really well why sevo, when introduced, immediately replaced halothane for gas inductions. In this particular picture, sevo is in yellow versus desflurane in blue, and you can see that desflurane achieves adequate depth of anesthesia more rapidly, though this is limited by pungency and likely not clinically advantageous in this situation. Other things impact the shape of the curve. Again, this is sevoflurane, the yellow line. Minute ventilation is the respiratory rate times the tidal volume over time. That's 1 minute. With higher minute ventilation, as evidenced by the green line, the volatile anesthetic achieves adequate depth of anesthesia quicker. With low minute ventilation, the red line, adequate depth of anesthesia is slower. So faster, deeper breaths, patient goes asleep quicker. I mentioned in the previous tutorial that a lot of patients are hyper anxious before going to the operating room. They can be hyperadrenergic, they can be generally freaked out, but it actually makes it harder for the patients to go asleep because their cardiac output goes up. Cardiac output is heart rate times stroke volume over time, that's a minute. And the impact of a high cardiac output is the opposite of high minute ventilation. The more sluggish the circulation, the lower the cardiac output, the more rapid the achievement of adequate depth of anesthesia in normal physiology. High cardiac output results in slower onset. The reason why increased cardiac output slows onset time is that large amounts of blood pass through the lungs per minute, and a huge amount of anesthetic is removed from the alveoli. Alveolar concentration rises slowly, the FA-FI increases more slowly, and brain partial pressure rises more slowly. The goal of delivering anesthetic agents intravenous or inhalationally is to achieve surgical anesthesia, and this usually requires using high initial doses of an agent to achieve goals and then reduce the dose to maintain steady state. Overpressure steepens the FA-FI curve, so the patient may receive, for example, 6% sevoflurane on induction rather than 2% sevoflurane during maintenance. Volatile anesthetics dissolve mainly in plasma but may also bind to red cells. Higher hemoglobin concentration slightly increases uptake. Hypothermia increases gas solubility in blood, and both effects slow achievement of adequate depth of anesthesia. Let's move on to steady state. Steady state exists when the alveolar concentration equals the inspired concentration. The net delivery of anesthetic agent equals the net uptake at your end tidal goal, and that is what you believe to be adequate depth of anesthesia. This is the plateau of the FA-FI curve. Now, this is not achieved during short cases, but what are the implications of this? For any chosen end tidal concentration, two equilibria exist. First, an early alveolar brain steady state or brain alveolar steady state, where FA-FI approaches 1 and anesthetic depth stabilizes. Much later, a total body steady state is achieved when all tissue compartments equilibrate to that same target partial pressure. Because tissue content scales with partial pressure and solubility, high targets produce greater total body loading and slower recovery. So at brain alveolar steady state, the FA-FI equals 1. The inhaled and exhaled volatile agents are the same. It's not a fixed concept. The steady state is always defined relative to the target partial pressure. For sevoflurane, for example, this may be 1.8% or lower, or 2.2% or higher. Be aware, particularly when you are giving relatively high doses of continuous volatile agent, that tissues begin to take up a significant quantity of gas. For tissue-soluble agents such as sevoflurane and isoflurane, reaching total body steady state implies equilibration of all tissue compartments to that target alveolar partial pressure. Because tissue content scales with solubility and volume, this results in substantial accumulation in slow compartments, particularly fat, which explains prolonged washout after long cases or high-dose anesthetics, why you might see 0.4% being exhaled from the patient long after you have stopped the sevoflurane. Finally, how important is the blood gas partition coefficient? For inhalational induction, it is very important, as the speed of onset determines the achievement of adequate depth of anesthesia. However, most patients undergo intravenous induction of anesthesia followed by delivery of volatile agents. So long as adequate depth of anesthesia is achieved before the effect of the induction agent wears off, the blood gas partition is less important. For short cases, brain alveolar steady state may never be achieved. Now let's review this tutorial. In this tutorial, we discussed the solubility of anesthetic gases and vapors in blood and plasma, that is the blood gas partition coefficient. Low solubility is associated with more rapid onset of action, and that is really important for inhalational induction of anesthesia. But other factors are important also: temperature, minute ventilation, and cardiac output. And I went on to discuss the FA-FI ratio and steady state. Next time, we're going to discuss drug potency, the oil-gas partition coefficient. I'm going to compare the different agents and explain why some agents are more potent than other agents. And I'll also explain why potency is less important than solubility and why this all leads up to the concept of the MAC, the minimal alveolar concentration, or the median alveolar concentration, depending on your perspective. I'll see you then, and I guarantee you'll learn something.